Okay, to pick up on the theme that we described here, assume that you have station and elevation information, including the elevation of the original water surface and the elevations of the center line of a pipe. And you are given that it is a free-flowing pipe. In other words, it's going to use up essentially all of its energy along the pipe except for what remains in the velocity. You do this by writing Bernoulli's equation, understanding that head loss is equal to FL over D times the velocity head times the length. But in a program, you basically mostly just sketch this out, and you're given a program Bernoulli's on this calculator. Now, Bernoulli's is going to need some inputs. Those inputs being your friction factor, the head, the length, and the diameter. Now, the friction factor is determined if you assume that it is turbulent flow. The friction factor is determined by the roughness divided by the diameter. So in this case, we're going to use a 1-foot diameter pipe. We'll see the data on the calculator in a little bit. It's rough concrete, and it has 500 feet of head to use. And the question is, what is the pressure? What is the energy grade line? What is the hydraulic grade line? And what is the pressure in the pipe at any point in the system? Not just one point, but any point. And you can do that by comparing graphs. You can do it with numbers and equations, but numbers and equations are nothing more than graphs. And so let's take a look at what the data looks like, because I'm not going to take the time to program it in. You use list 1 and list 2 for your station elevation. As you will see quite often, they're the easiest to get at. So if we just go to stat right here, turn on the calculator, we'll look at the data right away by going to stat and edit here, and you notice that in list 1 we've got data, that begins at an elevation of 3,800, I think I said 500, 3,800, and goes 4,000 feet over time, down to 3,500. So it has 300 feet of head. So your total head is 300 feet ahead. Again, you're knowing here, this is the elevation of the free water surface, and this is the center line elevation of the pipe. So you pre-input those, if you're smart, into list 1 and list 2, second quit, and you pre-store in your y variable Sx plus E, because the programs that are on the calculator will put S into the slope and E will be the more or less the starting elevation of the water. Finally, if you're going to do graphing, you want to make sure that you go to window, hit second quit here, you go to window and you make sure your window is set up, in this case from 0 to 4,000 for the X and from 3,000 to 4,000 for the Y. And you can change these numbers. Obviously you could actually make these here, we might as well look at it a little bit better. Let's make it 3,900 to 3,400, and you'll see a little bit of better look on your calculator. In this case, you're not keeping it as you usually do with 1.5 times the X of the Y, but you could. So once you get that set up, you go to the Moody diagram and you know, oh, if epsilon is the roughness, surface roughness of the pipe on the inside of 0.01 feet and the diameter is 1 foot, then my relative roughness is 0.01 and I have a friction factor in the order of 0.039. 0.039 for a relative roughness of 0.01. And so you then go to just to the programs and you go to Bernoulli's and you run through the calculation. Check that your revision date is correct. You had a pipe length, in this case it was 4,000 feet. The diameter was 1 foot. The friction factor we said was 0.039. The friction factor coming off the Moody diagram. The head available was 300 feet. and you end up with a velocity of 11.09, which is 1.9 feet of head. In other words, it burns up 298 feet of the energy loss in the pipe, and it remains with 1.9 feet of head, or foot-pounds of velocity energy per pound of material. You have a Reynolds number of about 1 million, so you're pretty certain, you're relatively certain here that this thing is going to be flowing quite fast. So you write down these numbers, hit clear, and you then go to program flow graph. 1.91 was the velocity. Flow graph will tell you to do what we just did. F from the Moody was 0.039. Your velocity is 1.91. Your diameter was 1 foot. Your elevation at the start was 3,800. And in this case, it's just, if you want to calculate a particular number, this is calculating the energy grade line, but let's go ahead and just let it know 4,000 feet later, which we know should be something like 1.9 feet. And if you notice there, it's 3791 because of this velocity, and we realize we input the velocity incorrectly. The velocity, if we remember, this was the velocity head. The velocity was in the order of something like 10. So let's rerun the program. And what you're doing here is you're putting a calculation here that you kind of know the answer to. You know that the answer here should be about 3501 because it's beginning at 3800. So let's see if we can try that again and do it right this time. Go to program Bernoulli's. The length was 4,000 feet. The diameter was 1 foot. The friction factor 0.039, because of that, was the flat spot on the 0.01 relative roughness curve. Head of 300 feet, and we had 11.09. So we'll try it again. Program. Flow graph. 0.039. Velocity 11.09. Diameter of 1 foot. Elevation at the start of 3,800. And distance from the beginning, we'll go with a full 4,000 feet. And we see we're kind of in the right range here. This had to do with whether or not we use the right number of sig figs there. This said, that gets us an answer at the end, but we might be interested in an answer anywhere in the middle. And so this is where you can now learn to use a great use of the trace function. So what we're going to do right now, we're going to go ahead and display the graph. Now the graph hopefully will be displayed correctly if you have your stat plot on, because that's going to graph and your stat plot is set up so it is doing L1 versus L2, or station versus elevation. So I'm going to hit second quit here. We'll do graph, and we have an error window range. So we're going to go and quit. Let's see what our error window range is. Second, stat plot. Those are all on. 0 on, L1, L2. Second quit. Let's look at our values. Stat, edit. We begin at 0, and our graphing goes from 0 to 4,000. Second quit. Window, 0 to 4,001. 3,900 is our minimum, which is not true. Our minimum on our graph should be 3,400, and our maximum should be 3,900. So you kind of got to learn where to look around. Second quit, and this time we graph and we see that there. Now, one is the elevation of the data we had, right? In other words, this is the ground elevation, and the other one here is the energy grade line.